All right, so in this video, I just want to talk a little bit more about Faraday's law. So on the screen, we have a B field that is into the page and it's increasing. And so far, what we have learned is that if we have a conducting loop, right, if I put a conducting loop, or it doesn't even have to be a conducting loop, it could be a surface like we looked at on one of the first days of the lesson, where we changed the magnetic field and we saw that there must be some kind of magnetic field being induced when the magnet would change speeds, right? I'm talking about the magnet swinging like a pendulum and then being slowed down by the conducting sheet. And we know now how to determine both magnitude of the induced current. So to get the magnitude of that induced current, you would find the induced EMF first, which is the derivative of magnetic flux with respect to time. And if you wanted I induced, you would just take that and divide by the resistance in the wire. That's Ohm's law. But what I want to talk about here is, let's go ahead and get direction too. So what direction is the current? Pause the video and figure that out if you want to. So we have a B field that is pointing into the page and increasing. To use Lenz's law, we are going to think about the direction of flux. So that's into the page. How is it changing? It's increasing. And so our thumb is going to point in the direction opposite of that change. So if it's increasing into the page, then our thumb is going to be pointing out of the page to oppose that change. And that's going to give us an induced current that is counterclockwise. So when we first started learning about current, way back in the circuits unit, we learned that what actually causes a current is electric fields, right? If you put a charge in an electric field, it's going to accelerate, and moving charge is current. When we place a static charge in a magnetic field, it actually doesn't do anything. So more directly, it's electric fields that cause current. And so the inference that can be made here is that there must be an electric field causing that induced current. And electric fields point in the same direction as current. And so we can assume that there must be an induced electric field that is tangent to this circle, this loop of wire at all points. So I'll just draw a few lines, a few E field vectors to show that. So E induced is tangent to that loop at all points. And so this is kind of interesting because now we're seeing electric fields show up in a completely different context than before. So we see electric fields in two different ways. E fields show up in two ways. So we did sort of the same thing when we first defined, when we first started looking at Coulomb's law and how there are forces on charges. We defined an electric field that's actually causing the motion of those charges, right? If you have a force on a charge, an electric force, just because that charge doesn't exist doesn't mean that there isn't something that would cause a force on that charge. And we're doing the same thing here. So now we've seen electric fields show up with Coulomb's law. So we have these Coulomb E fields that are created by, charges, other charges. And then we have a second way. So we have these non-Coulomb electric fields. And these electric fields are created by a change in magnetic field in this case, but we could say in general by a change in flux, change in magnetic flux. So that's kind of interesting. Now we're seeing electric fields show up in two different contexts, and this is just more evidence to these electric fields actually existing. And so So even if that loop of wire did not exist, we could imagine these electric fields being there. So I'm just going to erase our loop of wire now, and we're not worried about the current. And so now what you could imagine there are these electric fields that are pointing in the same sort of counterclockwise motion. So I think this illustration doesn't really do it justice. Let me just draw a few more electric field lines to show you this. So you can imagine this electric field existing in these concentric circles where our loop of wire currently is, but we don't need the loop of wire, and we don't need current because we don't need a conductor there. So you would see these circular electric fields throughout that region of changing magnetic field. And the direction can be found using Lenz's law as if there was a loop of wire there. And then what about the magnitude of that induced electric field? So what about the magnitude of E induced? Well, here's what we know from earlier in the year. We know that delta V, the magnitude of delta V, is just the integral of E dot dr. Okay, delta V is potential difference or voltage, and that's what E induced is. So we could write this in terms of E induced and say E induced is equal to integral of E dot dr. So what that says is, so this is really derived from finding the work done by the electric force around a path or throughout a path. So the path that you could pick here would be a circular path, right? Tangent to all those points. So I should have just left that circle up there. So there's our path that we are integrating around, and it's always going to be a closed path. So just like the notation with Ampere's law, we would have a closed integral of E dot dr. And so now this is the complete version. If I write the negative change in magnetic flux, this is the complete version of Faraday's law that now includes electric field if we are asked to find it. So there is an example where you need to find electric field using this formula, and everything works just like Ampere's law did. So go ahead and try that problem. I'll post it in the page that we're working in, and then I'll show the solution later.